Hi, my name is Eyüp and Aytaç. Today, me and my friend Erkani Mert Tosun will introduce our graduation project. As global waste expected to hit 2.2 billion tons by 2025 due to rampant urbanization, we need innovative solutions. Our research suggests using thermal cameras for waste separation as a cost-effective, precise alternative to traditional methods like sifting and magnetic separation makes it potential breakthrough to waste management. Project description. This project aims to classify and define objects with help of thermal imaging and machine learning classifiers. As it's shown on the table, every object has distinct emissivity values. These thermal characteristics of the objects can be easily observed and classified with the help of thermal imaging techniques and machine learning algorithms. Our experimental setup occurs with three Osram RAT 100-watt lamps, FLIR T420 thermal camera, and various municipal wastes to observe during experiment. By using thermal camera, infrared radiations of the objects are observed during heating and cooling processes.
Hi, I am Erkani Mert and I will explain solution methodology of our graduation project. The dataset for this project consists of recorded object videos with a 5-second initial display and followed by a 10-second heating period and concluding with a 10-second cooling period. The thermal videos for the dataset were captured in grayscale with a fixed temperature range of 15 to 45 Celsius. To estimate the temperature of objects, the average intensity within a defined region of interest was calculated. You can see ROI, and ROI is defined to cover most of the object and enable more detailed data. Each frame was filtered using a 5x5 Gaussian filter and to reduce noise, and we get the time series. Apply the low-pass filter, especially the hum filter, to remove further noise in time series, and time series in there that represent the pixel intensity over time. In this graph, we can see the heating and cooling curves of all materials types, and we will use these curves to classify objects. For feature extraction, the analysis involved identifying the highest temperature point in the time series, this is the red line, and examining 5-second intervals during both the heating and cooling phases. There are three methods for feature extraction. Method 3 was used for it because it was the best performing method among them and increases the estimation by looking exponentially backwards.
Training classifiers, machine learning. After feature extraction, label encoding is used to create machine-readable time series and output values, assigning integers to classes like metal is 0, plastic is 1, and carton is 2. The data is then reshaped for two-dimensional classifier compatibility with the machine learning and deep learning algorithms. Pre-classifier input data is shuffled to prevent bias and overfitting, improving model reliability and generality. These steps are designed to be widely applicable to various machine learning algorithms. In addition to traditional methods, we trained deep learning model for comparative analysis of various classifiers. Deep learning. Before training, deep learning requires one-hot encoding for output values because we use cross entropy as a loss function and it requires binary outputs. This function measures the divergence between true and predicted distributions. We trained multi-layered deep learning model with linear transformations and sigmoid functions for classifier comparison. After numerous trials, a 6-layer model transforming 8-dimensional input to 3-dimensional output was finalized. Training involved dividing data into batches, updating model parameters via forward and backward passes, and assessing performance per epoch. An optimal epoch number determined by training and testing accuracy helped avoid underfitting and overfitting, hence enabling the model to perform well on both known and new data.
Experimental results. In this project, we use 6 classifiers to perform the experiments. These support vector machine, decision tree, KNN, random forest, gradient boosting, and deep learning. For testing these classifiers, use the 30 time series, 10 from each class that are obtained from videos as described in previous section. None of the time series used in testing is used for training. Carton and metal classes are perfectly classified by all classifiers, while all the misclassification happened in plastic. We can see it on the performance graph. As it can be seen from the table, plastic is mostly misclassified as metal. Metal and carton classes are easiest to classify, while the hardest one is plastic. This is an expected result because heat capacity of plastic is in the between of the metal and carton. So it is expected to be misclassified. In this project, we succeed in classifying the materials with high performance.